Natalia, Evergreen Valley College. This is Astro 10, the online course. And this week we had we had our first midterm last week, and I will allow a second retake, not with the same questions, but the same content this week, and it's going to be on Wednesday. So some students, they miss the exam for various reasons. I recommend don't let for the last moment, because sometimes accidents happen, the computer's not working or internet fails or something else. So make sure you prepare yourself and try to run the exam as early as you can. This week also we are closing a discussion on astrology and astronomy. The main point of the discussion is to have each one of us to go to either Stellarium software and determine where the sun was the day of our birth, and compare that with the astrological sign. Are two the same or not? And if they are not, explain why and how far apart it is, and if there is any meaning being that far apart. But more than anything else, I have a question, a direct question, which is, do you think astrology is based on any truth statement? So provide what it is. So, or you think astrology is not scientific, in which case explain why. So when you provide arguments, make sure you provide arguments. It's not enough to say, well, I think astrology is a hoax because I learned that in my church. So you're not saying much. Or astrology is true because it works for me. I found my husband that is, is the sign that coincides with the sign that is complementing my sign. So this is not an argument either. You should provide either some statistics or some prediction 100% in a large percentage of population, not just, quite by chance. You cannot say that works for you and therefore it's true. I mean, this type of arguments are fallacies, and you must be away from them when you discuss this particular discussion, when you try to explain why it is true or not. We are also going on more specific aspects of our solar system this week, and that has to do with subject of chapter 7, which gives a brief overview of our solar system. What is important in chapter 7 is, first of all, the concept of differentiation. So write it down, differentiation. And if you always open a chapter and then you go to the glossary towards the end, well, this one I didn't find it, but that's probably differentiation is not in this section. So go to the next one. So chemical differentiation is the process by which a solid material, solid body like planet, at certain part in its history was entirely melted. And as a melted material, there you go. So you go to the end of it, and then you have the definition of this material. As a melted material, the heavier content sank down to the core, to the central part, and the lighter part of it stays floating on top. So chemical differentiation is this. So if you look at our planet, for instance, Earth has a core that consists of an alloy of iron and nickel. So these two heavy elements sink to the bottom or to the core of the planet, and silicates and light material like water, for instance, stay floating on top. The atmosphere, which is the lightest one, stays on the very, very top. So you might find these terms here and there, especially in the context of meteorites. So in addition to that, this chapter 7 also gives you the population, the type of objects you might find in our solar system. So we have, the sun, that's obvious. We also have planets. There are 8 planets, and some of these planets have moons. And there are also a population of asteroids, comets, and dwarf planets, and several dwarf planets that haven't been confirmed yet. Okay, so we are going through them and quickly see that most of the mass in our solar system resides in the sun itself, as you can see in this display over here. So 99.8% of the material in the solar system lies in the sun, and then you have some almost uh, trace amount in Jupiter, and everything else is all over the place. But it's not a lot. So when you think about major content, the sun, as far as mass is concerned, sun and then Jupiter. Now, this picture here describe um, in fact, the Starry Night software can show this as well. So if you go, um, if you allow for a display of inner solar system, let's see if it's gonna go. It's not going. So here's the inner solar system with the terrestrial planets, which is also a subject of this chapter to describe the main differences between terrestrial planets, those planets closer to the sun, and the so-called giant or gas giant planets, Jupiter, Saturn, Uranus, and Neptune. There stays further out, and you can't see in this simulation here. But in between the orbit of Mars and Jupiter, see these dots that goes around the sun, indicating that before or prior to the solar system formation, as we have in the simulation, the sun and the entire group of asteroids, as you see in there, the planets and the moons and the Jovian planets, they were all part of a circumstellar disk going around the central sun. And then when the temperature and the pressure were just right, this gas that pretty much made up the disk, this gas collapsed and came to form all the generation of planets we are used to, the dwarf planets and all of that we see in our solar system. Okay. Now, if I expand that to the outer view of our solar system, there you go. So Jupiter is here. We can't see the terrestrial planets now because they are too much close to the sun. Now, as you in the very far back in the background of this picture, it lies the star and the sun, and all of that is part of what we call Milky Way, and they all happen to go in a certain direction around the galactic center. And this is pretty much our 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 solar system is a small dust in what we call the Milky Way galaxy. And that is the picture that is being shown in here. Uh, Here is a representation of the Jovian or the Jupiter size or the gas giant planets Jupiter, Saturn, Uranus, and Neptune. And then Earth is shown here for as a way to represent its size in comparison with Jupiter's, about 1/10 of Jupiter's size as far as diameter is concerned. And here is a nice information that gives the size of these planets, the mass they have, and the density. The density is a very important factor, especially if we want to gauge what these planets are primarily made of. So what is the density? The density is a quantity in physics that gives the ratio between the mass content of the object or the material we are studying or the crystal we are studying. So the ratio between the mass of it by its volume, by its size, not the dimension, external dimension, but the volume. Um, and looking at these numbers, 5.4 grams per cubic centimeter, what we see is that Mercury, Venus, Earth, and Mars, they tend to have large densities, right? When compared with the density of Jupiter, Saturn, Uranus, and Neptune. So these four outer planets, they, as far as their content, as far as their chemistry, their the main or the dominant type of material they are made of, they are kind of a similar, you could say, but not at all comparable with the terrestrial planets. So these four planets, Mercury, Venus, Earth, and Mars, and also the moons that Earth carries, the moons that Mars carries, Phobos and Deimos. There are two moons that looks like asteroids that have been captured by Mars itself. Also the asteroids, all these billions of rocky type objects we call asteroids that lies in between Mars and Jupiter, all these objects, they are called terrestrials in the sense that they are rocky type. They are solid, and as you approach, as you go inward towards the sun, these terrestrial materials, they seem to be more metal rich than those that happen to be further out. Okay. And when you look at Jupiter data on its density, and as well as Saturn, Uranus, and Neptune, their density is similar to the density. Is similar to the density. Oh, my battery is dying. Just a second. Let me get a power cord. But the density of these objects is just a second. Alright, here I am. But the density of these Jovian planets indicate they resemble water. The density of water in this scale of grams per cubic centimeter is 1 gram per cubic centimeter. So you could say that Saturn, which has a density of zero point 0.7, if you could imagine place Saturn in a big ocean of water, Saturn would float because it's less dense than water. Um, but Jupiter would sink, and Uranus and Neptune would all sink in this hypothetical ocean. But astronomers can measure or um, or or have a gauge on the density by observing the orbit and the motion of these planets around the sun and using Newton's law we studied previously, and then we can get a hint of their masses. Since we can establish their sizes, then we can get the density, because the density is a ratio between mass, which you can derive from Newton's from direct application of Newton's law divided by the volume, which has to do with its content. Now, smaller members of our solar system are asteroids. That's one, um, and and here are. Oh, by the way, I will for midterm number two, and this is going to be part of midterm number two. I will take questions, develop questions based on the glossary of this book. So if you can review the glossary of the book and understand what those terms are, you might find questions on midterm number two directly related to the glossary. So when you ask me for a study guide, you can pretty much use the glossary for that purposes. Okay. Now, giant planets and terrestrial planets, they are different. So while terrestrial planets, Mercury, Venus, Earth, and Mars, and the Moon, and the asteroids, they are rocket type, they also happen to rotate not so fast as the Jovian planets, the gas giant planets. They rotate much faster, um, whereas the terrestrial planets don't. That's one striking characteristic. The next one is the amount of moons, the amount of orbiting moons. The, our Mercury, for instance, the planet that happen to be closest to the sun, has no moons. Venus, no moons. Earth has one, and our moon is quite strange because it's too big. It's too big to be one that was formed together with Earth. Um, so when astronomers brought rocks from the moon and analyzed these rocks, first of all. Second, when you take a measurement of the moon's density, um, all that information, the moon's density, the type of rock collect out of the moon's surface and brought to Earth, all of that indicates that the moon altogether looks like pretty much Earth mantle. And we are going to study Earth interior parts in the future. So Earth mantle is the region between Earth core, as I mentioned previously, is primarily iron and nickel, and its surface. So the mantle is the region between the lithosphere, which is the rock brittle surface, and the core. So the mantle lies in between. So the moon's material looks like Earth mantle, and that gave rise to a hypothesis for the moon's formation, in which Earth, a long time ago, when the solar system was still in the process of being formed, Earth had collided with a Mars-sized object, And out of this collision, material has then collapsed and formed perhaps one or two moons around Earth, and later on they joined into one. So the theories or the models differ a little bit. But why is that? Well, as these two objects collide, their core differentiation again, where the heavier part happened to be residing, the heavier part collapsed together, and the mantle spread outside these colliding bodies, forming therefore the moon, and the moon happened to be then formed out of Earth mantle. This is one of the current hypotheses. Um, So comets, so asteroids and comets. What's the difference between asteroids and comets? So first of all, their location. So asteroids happen to be primarily localized in between the orbit of planet Mars and Jupiter. So that's where the asteroid belt happen to be located. And people studying asteroids, they classify them by their chemical composition, first of all, but also by their dynamics. So there are families of asteroids that were originated out of a major asteroids that perhaps collided and broke apart in pieces, and then astronomers can trace down the dynamics, the orbit of these pieces, and trace down to a common origin, and then certify that by analyzing the chemical composition of each one of these pieces, and then certifying they are of the same family. Now, comets are different. Comets, they happen to be, most of them, localized in what's called the Oort cloud, which is a region surrounding the entire solar system in a spherical way, not just in the disk, but all over the solar system. And it lies beyond 50,000 AU to 100,000 AU, and is primarily made of ices. And another region is the so-called Kuiper Belt. So the Kuiper Belt, on contrary to the Oort cloud that goes all over the solar system, the Kuiper Belt is like a donut-shaped region where comets can also be found. Now, how can astronomers differentiate comets belonging to the Kuiper Belt and comets that belong to the Oort cloud or have originated in the Oort cloud? Well, the main reason is pretty much from the orbits of these comets. When when these comets come zooming by and passing in our solar system from all possible directions, not only in the direction associated with the plane of our solar system, but in a polar orientation, which means they came from not this donut-shaped region, the Kuiper Belt, but they came from the Oort cloud. Whereas comets that happen to be zooming through the sun or passing through the sun in a direction that's pretty much coinciding with the direction of the ecliptic, then those comets are said to be originated in the Kuiper Belt. So comets, asteroids. Now, how can we do the dating? How can we establish an age for these solar system objects? How can we give or establish how old our solar system is? Astronomers can use spectroscopy by observing certain transition lines in the sun that can trace the age of the star itself. There are certain lines, lithium is one of it, beryllium is one of it, and that these elements, as they circulate through the star, going all the way to hot regions and then up, they might be destroyed as the star evolves. And then by measuring their abundances, astronomers can, and with theory primarily, astronomers can establish some age for the star. And since we think the star was formed together with the planets and the moons, then if you establish the age for the sun, you can establish the age for everybody else. Okay, so this is one possibility. Another method, which is completely independent from this one, which has to do with stellar evolution, with the laws of physics governing the interior part of a star. Another idea or method is to collect rocks and date these rocks, pretty much using the same technique geologists use on Earth to determine how old certain environment or certain landscape is. So rocks that are used for these purposes, they must be volcanic rocks. And the reason is once the rock crystallizes, once certain unstable elements happen to be crystallized within the matrix of certain rocks, and astronomers collected these rocks by determining the ratio between byproducts of this atomic decay and their original population, parent rock by daughter rocks. By determining these ratios, astronomers can establish a precise age for that particular rock. So this is all true as long as there is no mixing, no erosion, and if you collect rocks that are out there in space, not subject to the erosional agents that we are so much used to here on Earth, like winds, like rain, like glaciers. So those don't exist in space. So once these crystals were formed out there in our solar system, and they happen to be embedded in meteors and asteroids and comets, that's it. So they stay their way forever, and the only major changes that will occur in there is their natural decay. And and again, elements that decay, um, geologists or physicists, they can establish the age in which this decay taking place if they are able to measure the amount of byproducts of this decay by their original atom. So those rocks are called radioactive rocks. And here's how it goes. So you take a sample of one of these radioactive rocks, and they all have tabulated what's called their half-lives. Okay, the half-lives. So we know how long it takes these elements to decay in byproducts. One example, um, the radioactive decay of carbon uh, carbon 14 is uh, is quite popular. The ratio between carbon 12 and carbon 14 is very much in use in to determine how old certain organic compounds exist. And a simple explanation to that is there is a constant ratio between carbon 14 and carbon 12. Carbon 12 is the stable part of the element. It doesn't decay, it takes a long time to decay. But carbon 14 decay quickly into other elements. So if you have a sample of gas that we breathe, so in that gas there is a small percentage of carbon 14 in the CO2. So we are breathing and breathing out CO2. So some of the carbon C that we breathe out, instead of a carbon 12, is carbon 14. So the oxygen doesn't know anything about 12 and 14. The oxygen like carbon the same way and combine with it. But 14 has a problem. It doesn't live that long. In about 6,000 years, 5,800 years, um, the probability of a carbon 14 still exists reduced to half of it. In other words, if you have a sample of carbon 14 um, in a in somewhere, So the amount of carbon-14 will be reduced uh, by half in about 6,000 years. Okay, so the ratio between carbon-14 and carbon-12 in living organisms doesn't change; it's always the same. Why is that? Well, because we eat food that has carbon, and which means we are assimilating a constant ratio of carbon 14 to carbon 12, and we eliminate also some constant amount of carbon 14, carbon 12, right? So our body is being recycled because we eat and because we eliminate. Okay, good. But what happens when we die? We don't eat anymore, right? So when we die, that's it. We are not eating anymore. Um, in our bones, you have calcium, and our tissues have also carbon, except that now in our bones, uh, the small amount of carbon 14 in it will be reduced to half in 6,000 years. And that is not being replaced because a dead person skeleton doesn't eat anymore. And then what happened? A geologist or archaeologist go there, or anthropologist, and take a piece of bone and take to the laboratory and then create a vapor out of that material, analyze and realize there is a certain percentage of carbon 14 that is not the same normal living organism has. And then by placing um, that percentage in this scale, it can determine how old how old that object is. For instance, if the ratio is 1/4 instead of a 1, so it means that in the case of carbon 14, if that is what we are talking about, that body has been dead for twice its half life, which means about 12,000 years. That's the idea, basically. Okay. Now, the Apollo mission brought several samples of moon's rocks to Earth and analyzed them consistently, and then were able to establish an age for our moon. And based on that, we agree, and based on other type of techniques, our solar system is pretty much at that rate 4.5 billion years. So the oldest rock on Earth, and this is very difficult because Earth has not only erosion but also has plate tectonics that recycles the entire surface. Earth oldest rock range in between 3.8 to 4.2 billion years, and that is in the region called shields, which are old regions on Earth. So glossary is in there. Glossary is in there. And now, an exciting aspect of this chapter is to explain how our solar system itself is started, right? How everything is started. Now, later on, we are going to explore the formation of stars. So, how the stars form. So, for stars to be formed, is require the existence of cold gas in the interstellar medium. Hot gas will not form stars. Cold gas are probable or amenable to form stars because gravity can act on it. And if the density of the gas is just right, gravity will slowly bring this gas to a contraction and to a collapse. And as it does, the central part of this system will be the local place of a future star. Now, this is one thing. The next thing you have to consider when you contemplate the process of star formation is that gas in general is not floating, doing nothing. So, as these giant molecular clouds that give rise to stars go about their business, orbiting the galactic center, they interact with one another. And as a result of this interaction, it creates rotation and vortex and all kind of instabilities in different locations. And and what I'm trying to say is that when this collapse takes place because of gravity, there is another component going on in the collapse itself, and that is the rotation. So if you happen to stay in the shore of a river that passes by, and then you look clearly to the river, the water doesn't flow laminarly. The water doesn't flow nicely, steadily, and organized and globally perfect all over the place. In fact, you see vortexes, you see rotation and convection in different places because there are resistance and rocks on the bottom of this hypothetical river. So, by the same token, as these giant molecular clouds orbit the galactic center, they are subject to kind of interactions with nearby stars, interactions with other clouds, and as a result, they have these uh, uh, vortexes as well. In other words, there is rotation going on. So when the collapse takes place in regions that will give rise to star formation, rotation is one of the components. And what happens as a result of it is that the collapse happens, but also rotation goes on. So when a star is formed, you have contraction and you have rotation. And this rotation will force the gas to settle in a circumstellar disk. Uh, I'm, I'm, I might have shown, oops, sorry, it takes years. I was buying a part for my dryer. Okay, so if you look, yes, loop, so give you an example of what that is. Video, maybe. There you go. So here is an example of a circumstellar disk and the star in the very center, right? And the star in the very center. And if you allow this to just keep on going, okay, you are a cool guy, but I don't want to hear you now. I just want to see the video, my friend. There you go. So you might be thinking why this disk doesn't reach the star itself. Well, it has to do with the magnetic fields of the star itself. They are too intense, and then it disrupts the disk, preventing the disk itself to reach the star. But what I want to show is this idea of a circumstellar disk and how this can be depicted. Not the one. Oh, I lost my file. Oh, you're still there. I think it's this one, isn't it? No. This one, maybe this one. No. Oh, there you go. So here are example of uh, clouds that might give rise to stars. So we think of stars since we were kind of a little kids. We look at the sky and we see these points of light, unchangeable. And if you are observant and you keep track of that every year, the impression is they never change. They're always the same. And in reality is they change. They are so far away, we can't pretty much perceive their changes, but they do change. And astronomers have tools, spectroscopy and photometry, that allow us or allow them to measure those changes. And um, but so stars have a beginning. The beginning is the cloud itself, a cold gas in rotation. And the stars, as we will study later on, about 1 month from now, they also die out. The energetic of stars eventually reach an end, and then they core. They create through nuclear reactions. They create new atoms, and pretty much that covers this chapter. Um, as I said, make sure some of the glossary questions are included in exam or midterm number 2, and then you can use that um, as a study guide. Okay. So let me know if you have any question, and it was a pleasure to be here with you. Okay, bye.